Thanks for coming back. The next session is on learning algorithms by Luke. Luke, thank you very much for joining us. I'm super excited to hear what you have to say about how we can learn learning algorithms. So over to you.
Yeah, thank you so much for the invite again. This has been a really fun workshop. So hi everyone, I'm Luke Metz, for those of you who don't know me. I'm a research scientist at Google Brain. And over the last, 2-3 years, I've been working on meta learning algorithms. So I'm hoping to tell you about some of that work. So as an outline, I'm going to first go over some motivation. I'm going to go over the family of algorithms that I've mostly been focusing on, iterative meta learning algorithms. I'm going to talk about some issues with outer training. And then I'm going to go into 2 instantiations of learned optimizers that we trained, task-specific learned optimizers, and some recent work on general purpose learned optimizers. Finally, I'm going to end with some discussion towards the future. But first, motivation. So as we all know, in deep learning, there's been this shift from hand-designed features to learned features. So we shifted from things like SIFT, HOG, to things like AlexNet and LINET. What I believe what's going on right now is a second trend. We're shifting from engineering learning algorithms to learn learning algorithms. So instead of hand designing things like SGD or like the concept of autoencoders, we're going to instead learn things. We're going to parameterize some function and then use that function to do the actual learning. And what this really buys you is it lets you design a higher level abstraction. In the same way that for supervised learning, we're no longer designing all the itty-bitty details of how these hand-designed features work. We're designing some high-level thing, and then we're letting optimization kind of fill in all the gaps. So we're designing these architectures, and then the specific weights are filled in by an optimization procedure. And I think this shift in abstraction is a really powerful idea. So currently, however, most existing meta learning methods don't really capture this goal. They're mostly synonymous with few-shot learning. So most of these methods focus on a very small domain of learning. And many of these methods don't really generalize very well. They're trained on relatively narrow distributions of tasks, and they're not flexible enough to target different model sizes, different distributions, things like that. It's been really refreshing in this workshop, however, because there's been a lot of work that's actually moving away from this direction. So I really appreciate a lot of the work going on and presented here. It's been my goal in this work to create generalizable, reusable, and robust learning algorithms. I want these things to be trained once, and then applicable everywhere. And applicable everywhere in that you don't need to even do any tuning. You just train something and then apply it wherever you want, and you'll get learning. So the family of learning algorithms that I've mainly been focusing on are iterative learning algorithms. And the reason for this is many successful algorithms we use today are iterative. So sort of the core of what we use to train these things are stochastic gradient descent methods. And these are all very iterative. You keep applying them over and over and over again, relatively simple, and you get these amazing results at the end. And some intuition on why these things might be better is, in general, it's very hard to learn without any kind of feedback. So let's say we're trying to minimize some loss surface that looks like this. We might start at this point, and we'll take like one step, go to here. Great. If you're just trying to do well on this loss surface, you have nothing to worry about. But let's say I give you this loss surface. Well, the point here and the point here look fairly similar. So maybe you'll take the same step. And in this case, you'll end up in a greatly subpar solution. Whereas if you had something with feedback or some iterative algorithm, you're going to actually do the right thing. You're going to continue to descend down this loss surface. So when I mean iterative, I really mean long iterative algorithms. So there's a bunch of existing iterative algorithms, things like MAML, for example, but those operate on a small number of steps, say 1 to 10 steps of training. The algorithms that we focus on take about 10,000 or more steps of inner loop to perform some computation. And usually if you apply them longer, they'll still improve performance. So in my work, I'm going to mainly be focusing on learned optimizers. I've been mainly focusing on learned optimizers myself for a couple reasons. For one, they're one of the most commonly used methods in machine learning and beyond. The ideas of optimization are very general purpose. Second, all these methods, as of now, that are commonly used are hand designed. things like SGD, atom, RMS prop, are all very simple equations, a couple lines long, and are all developed with using a mix of theory and engineering. I also think they're the perfect testbed to test meta-learning methods. They provide a pretty simple API. It's just gradients in and weight updates out. And there's already a lot of existing work on trying to understand how these things work, some theory around them, and so on. So they provide a really great and rich setting to test out these types of algorithms. So now I'm going to briefly walk through the specifics of exactly what I mean by how this learning happens. So, but before that, let's say we're just trying to train a simple model with weights W0. This could be parameters of a neural network, could be parameters of a linear classifier, it could be whatever you want. To train this, I might compute a gradient, multiply learning rate, and subtract from the original weights to produce some next update. I could do this over and over and over again to compute some trained model, W super n. At the end of training, I might want to measure performance. This is great. This is a sort of a hand design learning rule. What I mean by meta learning these optimizers is replace this update equation with some function, u. Takes as inputs gradients and weight values, and is parameterized by some outer parameters, theta. And now, after we've measured performance, we can use this measurement performance to improve these outer parameters. And we can do this over and over and over again. The y-axis here is outer training. It is the procedure of updating the weights of the learned optimizer to perform well after applying it. The x-axis here is inner training. Given some updatable parameters, we're going to update the parameters of the inner model. To summarize this computation in the equation, our goal is to find the weights of the learned optimizer over some distribution of tasks for some measure of performance. And in this case, this measure of performance is a function of the inner loop, which is applications of the learned optimizer. Now I'm going to go over how we actually train these things, some methods, problems, and solutions. So for people who have seen some learned optimizer work or have tried to do stuff like this, in general, auto optimization is really hard. It's really a pain and has this notorious reputation. And the reason it's so hard kind of makes sense. It's really, really expensive to compute a single outer function evaluation because it requires completely unrolling some optimization procedure to completion often. These outer functions can be noisy. So in the case of optimization, training a model will not get you to the same position with different random seeds, for example. And finally, these outer functions are really complex. They're formed by this nested or a composition of these update rules. So depending on how many steps you take, the more compositions you have of these. And because of this complexity, meta-learning approaches have kind of been limited. They haven't seen much success, and they've all required a huge amount of specialized tricks to make them work. There are two main families of methods people use to train these things. First is black box. This includes things like random search, hyperparameterization, reinforcement learning, evolution, things like that. And then the second is to leverage gradients. So you can note in this iterative composition of functions that if u is differentiable, this entire function is differentiable. It's kind of nasty, right? Because it's this iterative composition of applications of u, but you can still take derivatives with respect to theta. So what you do is you do something that we call unrolling the optimization. So you sort of lay out a bunch of these computations inside some automatic differentiation package. You compute gradients through this unrolled composition. Then you can just run SGD. And you do this over and over and over again to train the weights of theta. One common family of techniques people use with the gradient-based methods is truncated backprop through time. The key idea here is to split this sequence into multiple pieces. So instead of starting at W0, doing a full unroll to W8 and then backpropping, you split it up into 3 pieces, where you say just do 3 steps, compute a loss, backprop just this loss, and then essentially put a stop gradient here or don't compute gradients, and then do this again. What this gets you is it gets you many more gradients per full length of unroll. So now you're no longer only getting one gradient this entire sequence, you're getting 3. But it also gets you a much better behaved loss surface because you have less compositions going on. You only have 3 compositions of the update function here versus the full 9. Sadly though, this method is really biased. The gradient estimates you get at the end of it are not correct, right? Because this loss here is not depending at all about what happens early on in training. And in the case of learned optimizers, that's a very serious lack of information. So this leads to conflicting goals when you're selecting the length of these truncations. If you have long truncations, your gradients are less biased, which is great, but each iteration is slower. And your loss surface is horrible because you have these much longer chains. This leads to exploding gradients. If you have short unroll steps, everything's fast to train, which is great. You have well-behaved loss surfaces, but you have a lot more bias. So now I'm going to walk through 2 of these problems, exploding gradients and bias, to give a little more intuition as to what's going on. Before we get into a more complicated setup for exploding gradients, let's first consider this simple 2D loss surface, or sorry, 1D loss surface with 2 local minima. You're at this initial point here, and you're trying to optimize the value using SGD plus momentum. And in this case, there's only a 1-dimensional outer parameter, which is momentum. If I set a value of momentum too low, I'll end up here. I'll sort of go down and end up settling here. If I have a higher momentum, I'll make it over this peak and then end up in the second of the 2 minima. Great, this is all hopefully fairly intuitive. Now, what happens if we lay out all the trajectories for different values of momentum? So what I'm showing here on the x-axis is inner training step, and on the y-axis is the value achieved at the inner parameter. So with low values of momentum, shown in yellow, we can see that we end up doing exactly the same thing as I showed earlier. We sort of settle out in this 0 point, marked by this 0. The higher value momentum will end up in this higher point, because we'll make it over this hump. Oops. If we have an even higher value momentum, we're going to oscillate like crazy, and then eventually end up in one of the 2 minima. So what's important to note here is each one of these inner parameter values has a different loss value associated with it. The loss value of the first minima is 5-ish. This hump has a loss value of 11, and then this thing has a loss value of 0, which is the minima. We can plot these loss values now as a function of momentum at different points in time, which gets you this figure to the far right. And I want to zoom in on just this one particular point because it's most intuitive to understand. If you have small momentum values, we'll get a loss value that looks something like this, which corresponds to this minima. If we have larger momentum values, we'll end up here. But what happens if we have the momentum value right in the middle? So we're sort of getting up high and then kind of getting stuck there. Well, you can see these sort of spikes here. Now imagine trying to take a derivative right on one of these spikes. You can have a really bad time. It's going to be a massive value, which is going to hinder training quite a bit. And this is in the well-behaved case. As we go to higher and higher momentums, where we do get this kind of moving back and forth behavior, this loss surface becomes a mess. And trying to compute a gradient here, it's not going to work very well. You're going to get these really, really high magnitude values that aren't going to tell you anything about the direction you want to move. Like in this case, you really want to lower the momentum. But if you're over here, you're not going to really get any signal to help you do that. So this is a simple 1D example. What about neural networks? Does this stuff happen in neural networks? For that, we took a small MNIST network and trained it with Adam using slightly different learning rates. So in this case, the color here denotes learning rates that are basically the same, but different down to some small digit. And I'm going to plot different training trajectories for these different learning rates on 2 principal component axes. So at the beginning of training, these trajectories of different learning rates all follow roughly the same trajectory. But as we train more, they sort of split off and end up in very different locations. And what's important to note is that these different locations correspond to different values of the loss function. They might be similar, but they're still going to be different. And if we were to take a gradient with respect to someplace near where these forks happen, we're also going to have a bad time. There's going to be sort of really high norm gradients because the result here is going to be very different than, say, over here. So that was a hand design optimizer, so taking the derivative or looking at behavior with respect to learning rate. Now let's look at 2D slices of a learned optimizer. So right here, these are 2D loss surfaces taken from two directions from learned optimizer. Black here denotes good performance, so low loss, and white is high loss. If we do a single step or a couple steps of unroll, you see that we have a really smooth loss surface. This is great. We might be able to take derivatives here and expect to go from here, say, to over here. But as we increase the amount of unrolls, we start to see a bunch of structure appear. And this structure is going to greatly harm optimization. Because if we initialize here, for example, we're now going to get stuck at each one of these ridges. We're not going to be able to cross over each one of these small ridges. And this gets worse, more and more steps we take. All the way up to about 50 steps, where this loss surface starts to look like noise. If I were to take a gradient at one of these noisy points, it's not going to tell me even remotely which direction to go that makes sense. Like, I want to make it over here, but if I take a gradient here, it's going to be like some arbitrary direction because the noise is kind of dominating here. And so applying gradient-based optimization methods to this type of loss surface is kind of doomed to fail. So one solution to this is variation optimization, or also goes by the name evolutionary strategies. So if you squint at the past loss surface, it's almost like we want to smooth it. And that's essentially what variation optimization does. We're defining a distribution over parameters, and this smooths the loss surface. And then instead of optimizing just one point, we're optimizing over that distribution. So in equations, instead of taking just the loss, we're taking an expectation over a normal distribution centered on the current parameter value. And that expectation is over the loss value. So this is identical to taking a small Gaussian blur of the previous image. With this new objective, we're now left with a choice on how to do gradient estimation. There are two types of gradient estimators we can use. The first is a evolutionary strategies-based estimator. This is based on the score function trick or the log derivative trick, where you basically don't take derivatives with respect to the loss. So in that case, it's black box, but you do take derivatives with respect to this normal distribution. The second type of gradient estimator is a reparameterization gradient, which instead of where you do take derivatives through this loss surface, and you do that by splitting out the noise. So now you have the original parameters plus some noise contribution. Now, in practice, people often say, oh, the reparameterization gradient, you should always use it. If you can take a reparameterization gradient, it's going to be lower variance, you should use it. But in reality, this is not always the case. So for smooth loss surfaces, the reparameterization gradient will have much lower variance. This sort of matches our intuition, and everything's great. But for higher curvature loss surfaces, like the one we just saw, the ES estimator can actually have significantly lower variance. To give you a quick sketch of how this might be, consider a noisy loss surface that looks something like this. Lots and lots of local minima. If I already use an ES-based gradient estimator, it's going to look something like finite difference. So I'll sample 2 points, and then I'll compute some gradient that looks like this. Whereas if I have a reparameterization gradient, I will again sample points, but now I'm going to take the gradient at these points. And these gradients are sort of quite large. The gradient here is going to be quite large. So now the average of these points is going to have higher variance. And you can imagine, if I shrink the period of this, I'm going to make this gradient even larger. And it's going to just only increase the variance. So I can sort of make this arbitrarily bad. And in practice, when training learned optimizers, we do see these types of trade-offs. So early in training, the reparameterization gradient is much lower variance. It's like 10 to the negative 5 compared to ES. But at the end of training, we have extremely high gradient variance for the reparameterization gradient, but relatively constant variance for ES. And I want to highlight the y-axis here. This is on log scale. So what this means is at the end of training, we are 20 orders of magnitude worse if we were to train with pure backprop gradients than if we were to use just ES. So these differences are pretty significant and are sort of the difference between these types of methods working or not. The next problem I want to talk about is bias. So to get at this, I have another simple setup. Let's use gradient-based meta learning to learn a learning rate. So now I have a single meta parameter, the learning rate, and I'm going to optimize it via gradient descent with truncated backprop. And the results are shown here. So this dashed line here is the initial learning rate, and this other dashed line here is the optimal learning rate. This is a learning rate found via a grid search. And different colors denote different truncation lengths. What we find is that for short truncations, we actually go the wrong direction. So the gradients will take us away from the optimal learning rate and actually increase loss. For shorter truncations, we'll do go in the right direction, at least, but we don't converge to the right value. And only after going the full length truncations, in this case 10,000, do we converge to the right value. So this is obviously not ideal. The solution we have for this is to just increase the unroll length. So it's a fairly simple idea. First start out with short truncations, and then slowly increase the length of truncations to lower bias. The trick here, though, is that this is now actually possible. Before, people sort of conflated length of truncations with stability of training. You couldn't increase the truncation length too long because otherwise training wouldn't work out. You would have unstable dynamics because of the exploding gradient problem I mentioned earlier. But now that we have better gradient estimators, we can actually increase the length of the truncations. This sadly is still quite expensive. You're still having to compute these full-length unrolls. So it's not perfect, but this is the best we have at this point. So with that understanding in place, I'm going to go over the creation of two different types of optimizers to walk you through how these setups kind of work. The first is a task-specific optimizer. The intuition here is we wanted to get at if any of this is worth any of our times, basically. If we can not train a task-specific optimizer to achieve enough performance or to do well enough, there's no point in trying to push this further. Like if it can't overfit to one task, there's sort of no hope that these methods will work well for more general purpose applications. There are four main components of these types of learned algorithms. There's the architecture, or four main choices. There's the architecture, which is how the learned optimizer is parameterized. There's the task distribution we're training on. There's how we measure success, or the outer objective or the meta objective, so what we train our optimizer to do well on. And then outer optimization, or how we actually update the learned optimizer parameters. All this work and this optimizer is pulled from our recent paper. So if you're interested in more details, please check that out. Cool. So the first thing is architecture. In this problem, we wanted to pick an architecture that had a good inductive bias. It was also very fast to compute. So for that, we picked a tiny MLP. The inductive bias comes in on the inputs. So in the case of this MLP, we feed in gradients, momentums, time steps. And the fast to compute comes from the fact that this is a one hidden layer MLP with 32 units. It's super small. And now this MLP is applied per parameter. So what this means is if we have, say, an n-dimensional inner problem, I'll do n applications of this small little MLP, each of which with shared weights. And then this MLP outputs a change in weight. For task distribution, this defines the type of problem we want to do well on, or the types of problems we're specifically targeting, or the objective we're specifically targeting. We have a few choices here. Oh, sorry. To form this task distribution, we take the ImageNet dataset, which has 1,000 classes, and we split it up by class. So we take, say, the dogs, cats, whatever, on training set, and then we have some separate held out set of tasks or classes for the test set. Each one of these classes has some inner training data, as well as some inner validation data, because ImageNet has two splits. There's a training split and a validation split. To sample tasks from this, we sample 10-way classification problems. So sampling, say, 10 of these training classes and 10 of these training classes. each one of these problems now has 10K images, training images, and 1K validation images. So if people are familiar with the mini ImageNet setup, this is a similar way of constructing dataset splits. But unlike mini ImageNet, we're using the entire set of training images and the entire set of validation images. It's not just these 5-shot, 1-shot type problems. And with this dataset, we're training these small little ConvNets. The input is 32 by 32, so it's resized. Run through 3 conv layers, and then we do a linear projection to the output. We're using cross entropy loss on the inner loop. Now, for an outer objective, this is picking what we actually want our optimizer to perform well on, and we have a couple choices for this. We can optimize our optimizer to do well on training loss, for example. This makes sense if you think about our optimizer as an optimizer. Optimizers should minimize the thing they're trying to minimize. Great. But if you're from deep learning, you have to know that that's not the whole picture. You have to only care about, say, validation performance, which you can only measure with held out data. But we don't have to stop there. We can actually get more creative. So we can measure performance, say, on a different distribution of data. For example, we can train optimizers to learn classifiers that are more robust or better at out-of-distribution generalization. This is something we explored briefly in this paper, which was a workshop paper. But for now, we're just going to do this the simplest thing. We're going to train an optimizer on training loss, and we're going to train an optimizer on validation loss. Now, usually when I say, oh, we're going to meta-train on validation loss, people get concerned that we're kind of overfitting or going to cheat somehow. So I wanted to lay out exactly what we mean to show that we're not cheating in any way. So when we're training our learned optimizers, we're using the outer training distribution. And this contains both training data and validation data. So what this means here is we'll say, or to lay this out here, we'll take our initial weights, W0, and then we'll compute gradients with the training data to make us go to W1 and so on, only using training data. The validation data is used only to evaluate performance of the optimizer. And when we do make updates with this validation data, we're targeting the learned optimizer weights, not the inner problem weights. And what this means is at outer test time, we can use this held out set of tasks. Neither the training images or the validation images have been seen before. And then only use the training data piece of this, because that's all our learned optimizer needs to have access to. And then when we evaluate, like we do in standard supervised learning, we can use the validation data. But we're never actually taking updates based on the validation data. We're only taking updates based on the training data. Last but not least is outer optimization. In this case, we're using a truncated gradient-based method. We're scheduling the length of truncations from low to high, and we're using the variational smooth gradient estimator that I mentioned earlier. In this case, we use a gradient estimator based on a mixture of evolutionary strategies and backprop gradients. To summarize, we're trying to find the weights of our learned optimizer over some distribution of tasks, in this case 10-way classification problem sample from ImageNet. Our outer objective is training loss or validation loss, and we're doing this over some inner loop, which in this case is applying the learned optimizer to train some small content. To evaluate this learned, now that we've had this set up, let's look at how this thing performs. I'm going to take a particular instance. I'm going to sample one outer test problem and then show learning curves for our learned optimizers, one training against training loss, one training against outer validation loss, some learning rate tuned baselines, which are these next 3, and then 2 baselines that are sort of hyper-tuned. These things are 8 parameters. We spend a ton of compute to tune these things. This is sort of the best you can hope to get with hand design optimizers. And what we find is our learned optimizers do pretty well. So here I'm showing training loss, and we see that our learned optimizer is performing much better than the learning rate tuned methods, and then better again than this sort of hyper-tuned method. I want to call it one thing. The x-axis here is wall clock time. So not only are these things performing better on step time, they're actually helping us train faster than we would otherwise be able to train. So this was training loss. Now let's look at test loss. And we see a couple interesting things. First, we notice that these training loss curves, both the learned optimizer and Atom, promptly overfit, which is kind of cool. Because when we're doing well on training loss, this doesn't actually generalize. The solutions found by this thing, despite reaching them quickly, are not good solutions. But now if we take instead the learned optimizer trained to target validation loss, this orange thing, we see we once again do pretty well, where we reach a lower minima than the other baselines, including the hyper-tuned Atom baseline. So this provided us with enough positives, I guess, to take this further. We sort of saw the gains that we could get with a single optimizer, and we decided to push to see how far we can make this to go to general purpose optimizers. The key idea here is that we want these things to work on. So what it means to be out of distribution in this sense, what we want in a general purpose optimizer, is that this problem will just work anywhere. You can take an optimizer, apply it to any new problem, and it'll just work out of the box, requiring no tuning whatsoever. So we can take our past optimizer and see how far we have to go, right? The previous optimizer can be applied to whatever we want, but it might not necessarily work very well. So we can test how it works on a couple problems. First, we try transferring from a ConvNet where it was trained to a fully connected network. And we see meh performance. It kind of works, kind of optimizes, but nothing to write home about. It does about as well as learning rate tuned Atom. But for other problems, we see something much worse. In this case, we're transferring from ImageNet dataset to applying it on MNIST. And we see our two learned optimizers diverge very quickly, in fact, whereas the learned optimizers, whereas the learning rate tuned optimizers perform much, much better. It's obviously not ideal. So anyone who's familiar with machine learning in general might note that, of course, this makes sense. You're training on a single task, right? We're only training on these small little ConvNets on ImageNet classification. So being familiar with past years, we did the natural thing, which is just make our data set much, 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 much larger. So in this case, 5,000 times bigger. We did this in another paper that and released a data set called TaskSet. And what this is a distribution, is a data set of tasks. And I'm showing here is a t-SNE of that data set. So how this is constructed is I create a feature space that is based on performance of hand design optimizers. And then I do a dimensionality reduction. So points that are similar to each other here are going to mean that similar optimizers perform well on these types of tasks. And there's already some structure emerging. So for example, these green models over here are kind of a funky masked autoregressive flow models. These blue models here in this clump are all character, RNN language models, and so on. These tasks, so they're obviously way too many to create by hand. So we sort of use a mixture of procedurally generated and with hand designed pieces. So first, there's 3 stages in how these tasks get created. First, there's these samplers, which are pieces of code that sample basically task configurations. So in this case, this is the code to sample a ConvNet. We might sample a number of layers. We might sample stride pattern. We might sample hidden units. We might sample activation, initialization, padding, dataset, and so on. We run these samplers to sample a bunch of tasks. These give us these configs, which are basically the everything we need to know about how to construct the task. And then these configs get fed into some code, in this case, Sonnet TensorFlow, to produce some models that we can actually train. In terms of the variety of tasks, there's a couple of, many different types of sample tasks that we use. We have a bunch of image supervised learning class tasks. We have a bunch of image unsupervised tasks, so things like autoencoders, variation autoencoders, some flow-based models. We have some language tasks, as well as some synthetic tasks. We hope that as we sort of continue to develop this set will grow, but for now it's relatively small, because these types of tasks all require a bunch of sort of hand design work, a bunch of me writing samplers, configs, and things to actually make these models. The key idea here when designing a task distribution is we really want to care about outer generalization. So we want to be able to transfer to new tasks. So ideally, we just train on targets or train on tasks we actually care about. So in this case, I'm saying like large ResNets, large transformers, like larger scale problems that people actually do research on. The problem is this is really, really expensive. If we try to meta train on these types of problems, it's going to be nowhere near feasible. So we have to make some trade-offs. We need to be large enough so that the signal we get for meta learning is actually useful for these larger tasks, but still small that it remains computationally efficient. So we picked a trade-off. This trade-off is roughly based on the idea that we want to train in under an hour. So we want each task to train in under an hour on a CPU, which makes meta training a lot more efficient. But as a result, the types of models we consider are relatively small. So here is the log parameter count, and we can see most of these models are under 1 million parameters. And it's to make this training much smaller, much faster. So going in, our hypothesis was that adding more tasks would lead to better meta-generalization. And we can just directly test this now. So on the x-axis here, I have the outer training set size. On the y-axis, I have the outer loss on some test set of tasks. So this is generalizing to some new set of tasks. Each star here represents a trained learned optimizer. Now what we find is the more tasks we add, unsurprisingly, the better we do on generalization performance. What surprised me, though, is at the scales of these x-axis. So if you would ask me ahead of time, like how many tasks I would think we would need to train optimizers, I would have said, oh, only about 100 would really be required. There's not too much going on there. They're relatively simple problems. We probably don't need a ton of diversity. But what we find is that even after 3,000 tasks, we're still improving on generalization performance. The next thing we did to try to get towards general purpose architectures is improve the general purpose optimizers, is improve the architectures. So existing work, or most existing work, uses relatively simple parameterizations of optimizers. So I already described this feed-forward MLP optimizer, but there's another family of optimizers people also use, which is sort of the original work by Marcin, gradient descent by gradient descent, which just takes a gradient, feeds it into a per parameter LSTM, and then outputs your weights. So both of these operate entirely at a per parameter model. So there's no types of like shared compute going on. It's all split across this network, and each of these pieces is relatively small. So in this work, we explored a hierarchical model where we have a per layer LSTM, which takes in summary features, so things like gradient norms, loss values, and so on, and then outputs information to a per parameter model. In this case, the same model we have here. I want to highlight one thing, which is these things actually have access to loss values. And what this means is these optimizers can start to act the way humans do. When humans train a model, they'll look at training loss and validation loss, and maybe see, oh, there's some overfitting. Let me add some regularization. And this per layer LSTM can do the exact same thing. It can sort of turn on more regularization, so we'll overfit less because it has input to these features. Unsurprisingly, because these are in these slides, we can see improvements from this new optimizer. So in purple, this is the original work, this LSTM-based optimizer. In red, or sorry, in orange, I have the per parameter MLP. And then in blue, I have this new hierarchical model. And this plot is just a training curve of learned optimizers. So outer parameters, or outer training iterations on the x-axis, and the evaluation losses on the y-axis. And we find that, unsurprisingly, this hierarchical model performs better. This might not look like a huge gain, but if we look, say, at 5,000 steps, it would take 15,000 steps, roughly, to reach that same point. So these things are training roughly 3 times faster. Finally, the last thing we did is really up the compute. So the original work used roughly a GPU day of compute. Our follow-up work used roughly 1,000 CPUs for 5 days. And this newest work uses somewhere between 20 to 40,000 CPUs for 2 to 4 weeks. So it's a considerably larger amount of compute time. And with all these compute and improvements, things are starting to get interesting. We're starting to see some stuff that's exciting in my mind. But before I show you results, I want to first say that comparing optimizers is hard. There's a lot of papers that try to do this, and it's sort of a very fraught thing to do because there's a lot of sticking points or things that you need to take care about. And because of that, comparing learned optimizers is like even harder. It's now you have to worry about training distribution, how far away you are from the training distribution, and so on. So this is the best we have at the moment. The first thing we want to compare against is to see performance of a as compared to a simple learning rate tuned atom. So what we do is we pick one learning rate and then check performance on a large mixture of tasks, in this case 100 tasks. And what I'm showing is I'm showing performance deltas with a learned optimizer. So if you perform to the right of this dashed line, you're performing better than the learned optimizer is performing better than this learning rate tuned atom. To the left is worse than this learning rate tuned atom. And I'm showing two different distributions of problems we test on. There's an IID distribution, so this is part of the training distribution. And then there's a test distribution, which is a slightly different distribution of problems that have not been seen during training. And what we see, as compared to a single trial of atom, we perform better. Great. But in practice, people often don't do just a single trial. They'll do some tuning. So now we can compare to doing tuning on baselines. So for each of these problems, we're tuning a learning rate. And now this is somewhat cheating for our baseline because this is using 14 trials, whereas we're just using one trial. So one optimizer doesn't need to be tuned. So we see that performance for the baseline, so the number of models that do better with the baseline, or the gap between our learned optimizer and the baseline starts to shrink, as denoted by these bars moving to the left. But we still are doing better on over half the problems. Our learned optimizer is doing better on over half the problems. And this trend continues with sort of more extreme tuning strategies. So now this last column is 2,000 trials of different, 2,000 hyperparameter combinations. And we see that even after doing this extensive tuning for our baselines, there's still problems our learned optimizer performs better on. Next, we explored some added distribution generalization in a more controlled setting. I'm running short on time, so I'm going to gloss through these quickly. But the high-level idea here is we train on this shaded region here, and we're going to vary one parameter of the inner problem. So in this case, number of hidden units. The different models here, or the different colors here, denote baselines of different learning rates for atom. And what we find is that even outside the training distribution, our learned optimizer performs sanely. This only happens up to a point. So here, for example, if we make our networks too big on CFAR, we might diverge. We see a similar type of behavior happening with batch size, where in the training distribution, we perform pretty well. Out of the training distribution, we continue to perform pretty well. In this case, the gains start to shrink. And if we train on really, really small batch sizes, we might diverge with our learned optimizer because it's so out of distribution. We tested this guy out on larger problems now. So we can take our learned optimizer and apply it on, say, a 14-layer ResNet trained on CFAR 10. And we see pretty good performance. We're comparing here to learning rate tuned atom and learning rate tuned momentum. So we perform about as well as atom and momentum at the minima. Can do the same thing on ImageNet. And once again, we see we perform about as well. So I wouldn't take these as, oh, our learned optimizer is better or worse, but it like performs comparably with what you might do in practice. Finally, an experiment that excites me a lot is we can actually train these optimizers to train new versions of themselves. So I have a problem, right? I'm training a bunch of learned optimizers, and I have this magic optimizer. Maybe it can help me do my research. So what I'm showing here are outer training curves. X-axis is outer training iteration, y-axis is outer loss, and I'm comparing two things. In orange, it's what we use to actually train these things. So this is like atom tuned learning rate. Whereas in blue, we show the learned optimizer. And we see it actually performs a little bit better, or about the same as what my best tuning strategy was to actually train this thing. So this is exciting. So originally my goal was to get these things to the point where I'd want to use them for my research. And I would say it's almost there, but not quite. There's still some issues, still some things where these optimizers don't work flawlessly. So running short on time, but I wanted to briefly go over where I think this stuff's going and hopefully seed the discussion with some thoughts and questions. So I think in general, the future is pretty bright. I believe we're on the brink of an AlexNet-like moment here. Like I think once we can start to show these things perform really well, we'll start to use these things to perform to optimize themselves and so on, and we'll start to get much better performing systems. But I also think optimizers are just the beginning. There's a lot of other interesting types of iterative meta learning algorithms I think we can learn. There's been a lot of work in general, and in particular in this workshop, discussed about reinforcement learning algorithms. For example, discovering reinforcement learning algorithms of all policy gradient or meta reinforcement learning. Another area I'm particularly excited about is unsupervised learning or semi-supervised learning. We've done some work in this space, but I think that there's still a lot more that can be done. There's also a lot of other kinds of problems. In general, if there's a problem that we can measure performance on, or a task that we can measure performance, but don't necessarily know how to do well on, these are sort of an ideal fit for meta learning methods in general. There's a lot of work to be done still on learning architectures. So the key requirements here is these architectures must work on a wide variety of settings, different inputs, different targets, different domains, and so on. And then there's been proposed a lot of different types of solutions to these types of problems. And it's sort of unclear at the moment which types of solutions perform better. I talked to you mostly about per parameter models. There's also a whole family of graph neural network or multi-agent models that have shown incredibly strong generalization performance in a wide variety of setups. This is sort of the approach that Badger-style architectures make, for example. They have shared weights, and they're communicating in this multi-agent setup. There's also things like cellular automata, for example, which you've also seen a talk on, or neural computers, things like that, which also have pretty good generalization performance and are another way to set these things up. There's also a whole other domain. You can use prognosis / discrete search, which we've seen some stuff on as well. The next big open question is, what do we actually train these things on? Or is that even the right term to think about? Should there even be a training set? Like what's the perfect distribution of tasks? Should there be something dynamic? Should there be more curriculum here? Should we throw our ability to make the data sets out altogether and make it some open-ended process where we have some agent or something creating data sets to train on? And finally, something that I'm excited about, this is also, is can we use these methods to enable new things? The question that I've been thinking about a lot recently is, does working at this meta level actually buy us anything? Like, does this get us anything that we couldn't already do? Does training an optimizer to solve a problem help us better than if we were just solve the problem itself? And then finally, can we use these optimization procedures to teach us something about learning? Like, can we go train one of these optimizers and sort of poke and prod at it to come up with insights that we can then transfer back in some hand-designed way? So I want to thank my awesome collaborators throughout this project. It's been a lot of fun to work with them all. And with that, I'm happy to take questions, discussion, or whatever else. Thank you all.